Okay, welcome to your first chapter of Flipping the Classroom. These are your notes for tomorrow's class. Today we will be discussing points, lines, and planes and their attributes. So get your notes out if you haven't already. Okay, remember we're going to be taking them in Cornell format. I will help you along as we go through these first few lessons together. Okay, after that I will quit giving you so many instructions, assuming you will know how to do it. Okay, also, please keep in mind, press pause on the video anytime you need extra time to copy something down. I'm going to go fairly quickly so that the video doesn't run long or have dead air places in it where nothing is actually happening. Okay, the very first thing you need for your Cornell notes is you need an objective and a lesson date. Okay, today is September 4th, but the lesson will actually be happening in the classroom on September 5th. So that's your date. And the objective is the student will discern the difference between Euclidean and non-Euclidean geometries and learn the basic geometric structures. If you're not familiar with the word discern, it means kind of like to tell the difference. The student will tell the difference between Euclidean and non-Euclidean geometries and learn the basic geometric structures. Pause the video if you need to, and then press play when you're ready to move on. Now, the title and the objective referred to Euclidean geometry. A little bit of background information here. Back in about the 3rd century, a lot of mathematicians were beginning to tackle a new version of mathematics that would eventually become known as geometry. Euclidean was the mathematician that kind of gathered all of the information that people were putting together around the world, because it's not like they had the internet to communicate with each other or anything like that, so they were disconnected from each other. He kind of pooled all of the information that they had, gathered it all up, and he constructed several chapter type books which he referred to as the elements. Okay, and Euclidean's basic idea was geometry was the study of flat space. And at the time, that was a revolutionary concept. Here in recent centuries, we've come to realize the truth of it is that, it's not flat space. Okay, the three-dimensional world has curves and uneven surfaces and things like that. But in Euclid's point in time, okay, this was the idea, and it held all the way from about 300, year 300, until the 1800s. The study of flat space, as I said, is based upon the Greek mathematician Euclid, and it says book, but there were actually several of the books, and they were titled The Elements. Euclid's theories and postulates and definitions and all that kind of stuff, okay, are all constructed on what are definable terms and also undefinable terms. Okay, things that we can put a precise definition on, and other things that are more difficult to actually define. And we'll talk a little bit more about that as we go on. The flip side of that, as in recent years, the last 150 years or so, we have started to run into non-Euclidean geometries. The most prevalent one in flat space, to disagree with Euclid, is what they refer to as taxicab geometry. It's not the only kind of non-Euclidean geometry, but it's the only kind of flat space geometry. On the left hand, you are looking at a diagram of what Euclid would refer to as distance. And you've probably heard the straight up definition for distance plenty of times before. The shortest distance between 2 points is a straight line. That is based upon Euclid's books, The Elements. Okay. However, modern geometries have come to accept the fact that sometimes 2 points cannot be connected by a straight line. There is some sort of an impediment, something that you cannot get around by simply drawing a line straight through it. And an example is what they call taxicab geometry. If you think about a car driving along streets, if you want to get from point A to point B, you cannot simply take off in a straight line at point B, ramming through other cars, smashing through buildings, stuff like that. We have to make twists and turns in order to get from point A to point B. And that often involves basically, as you can see on the right-hand diagram there, kind of like driving along streets, making right and left turns, 90-degree turns, and there's no one set way to get from one point to another, but there are several options that you have. The rule basically is, as long as you continue from one point to the next without doing anything goofy or going out of the way, that you will get from point A to point B, and that distance will be the same as anybody else going from point A to point B, as long, again, as long as I said, as you don't go out of your way to get from point A to point B. Okay, so in your left-hand column there, you should have Euclidean geometry and non-Euclidean geometry. In the right side, you should have the supporting points, like Euclidean is study of flat space, Greek mathematician, the elements, constructed on definitions and undefined terms. Non-Euclidean in the left-hand column, okay, taxicab geometry, probably also in the left-hand column. And if you chose to do the diagrams, they might be in the right side of your paper. Pause the video if you need to. Okay, now the basic structures in the world according to Euclid, and that is what this class is based upon. We're not going to spend a whole lot of time talking about non-Euclidean or taxicab geometry or anything like that. We are studying Euclid's geometries. Okay, and in the world according to Euclid, everything could be broken down into three basic structures: the point, the line, and the plane. We're going to get definitions to go along with point, line, plane here in a minute, so you might hold off just a minute on where you actually put them. Okay, here's your first term. A point, we have a definition, new term. New terms go on the left column. A point is an object that exists in zero-dimensional space. It has no length, it has no width, and it has no depth. In all reality, a point does not even exist in our three-dimensional field of vision. We can't even see it. Okay, we have to actually draw it, you know, enormously larger than it actually is, just so we can see the thing. Whenever we discuss points, we're going to call them by their name. Their name, the name of points, is always a capital letter. This is supporting information. This should go over on the right side of your notes. Okay. An example would be something like that. When you see it in a picture, you will see either a full circle or possibly an outline of a circle. Next to it, if it has a name, you'll see a capital letter floating somewhere near it. And anytime you refer to a point out of a diagram, you'd call it point, and then you state its name. So in this case, point P. If you have need to refer to it in writing form, okay, in the middle of a full sentence or something like that, you will actually write out point P. Don't just throw the letter down there, actually identify what type of a structure it is, and then its name. That is how we're going to identify many of the things that we look at in geometry this year. The next object, a line. Line is a new term. It goes over on the left-hand side. Over on the right side comes its definition. A line is an object that exists in first-dimensional space. Unlike a point, a line has length. However, it has no width and it has no depth. Okay. As you probably know, lines continue infinitely in both directions. And the basic rule of thumb is that it takes at least 2 points in order to construct a line. When we discuss lines, once again, we will call them by their name, which is always the name of any 2 points that are on the line. Okay. There's what a line might look like. So we said it requires at least 2 points in order to construct a line. So we have 2 on the line. There may be more. Does not matter if it's more, if there are more. But we describe a line by naming the 2 points and also calling it a line. Okay, so particularly we are looking at line AB or line BA. It does not matter which order you get them in. However, it is slightly more appropriate to list your points alphabetically. And most often, if there are more than 2 points, they will pick on the 2 points that are on the outer edges. So if there were points that were in between A and B on this diagram, they would probably still call it line AB rather than picking on any of the points that were in the middle. If you need to refer to it in writing, we have a little symbol that goes along with this. What you do is you list the 2 points that you have, AB or BA. Again, slightly better to do it alphabetically. Okay, but if it is a line, we will put a little diagram of a line over the top of it. Okay, so a little line, arrows on both ends, because of course lines continue infinitely in both directions. Another definition on here, just something extra. If 2 or more things were to exist on the same line, they are what we refer to as collinear. Okay, tough word to pronounce there, but collinear is the correct way. Okay, a ray is a different kind of a line. Okay, a ray is a line that only continues in one direction. You're probably already familiar with what a ray is. The end that does not continue infinitely is called an end point. So while a line goes infinitely in both directions, a ray will have an end point, and the other direction will go on infinitely. When we discuss rays, we call them by their name, just like everything else, which is always the name of the end point and then any point that is on the ray. With a line, we said it really didn't matter which 2 points you picked or what order you put them in. With a ray, it is very important which at least one of the points and what order you put it in. This guy can only be called ray AB. A gets top billing because it is the end point. This one has absolutely nothing to do with being alphabetical. The ray gets the end point first. We have a symbol for this one also, as you might have guessed. Okay, when you write it down, you can name the 2 points. Remember, the end point goes first, and then any other point that is out on the ray. Okay, and the little symbol that goes on over the top of it, again, a little line, but only an arrow. And of course, the arrow is pointing in the direction that the ray is going. A does not get the arrow because A is the end point. B gets the arrow because that's the side that continues on infinitely. Here's a term that pops up every once in a while. It's called opposite rays. Opposite rays are rays that have the same end point but proceed in exactly opposite directions. Opposite rays, it's kind of one of those things, it's surprising that we even have a name for this, but there you have 2 rays. The red one on the left, which would be ray BA. Again, B gets the first billing because that is the end point, and on the right side, the blue one is ray BC. Okay, those are opposite rays because they both begin at the same end point, which is B, and then they head exactly away from each other. I say it's surprising that we even have this term because in all reality, what does this figure look like? It looks like a line. We could have just as easily called this line AC instead of 2 different opposite rays. But the term does exist, so now you know it. Okay, another different type of a line that we have, and you're probably familiar with this one as well, is a line segment. A line segment is a line that does not continue in either direction. And of course, if it doesn't continue in either direction, then it has 2 endpoints. When we discuss line segments, we will of course call them by their name, and their name is always the name of its 2 end points. So in the case of the diagram that you're looking at there, this would be line segment AB. And it still is correct to refer to it as line segment BA. Does not matter which order we get them in because it has 2 endpoints, so they could honestly both get the first billing. So it doesn't matter one way or the other, but you will tend to see it alphabetically rather than not. So usually that will be line segment AB. Similar to the line and the ray, we have a symbol that goes along with being a line segment. And you could probably guess it is a line that does not have an arrow on either end because line segments do not travel either direction. If you need to refer to it in writing, you will write line segment AB or line segment BA. Okay, when we run across the situation where 2 points are listed back to back with no marking over the top of them, this is speaking about the distance between the 2 points. We saw the little line notation. The little line has arrows on both ends. We saw the ray notation, a line that has an end point and then an arrow on the other end. We saw the line segment notation, a line that doesn't have arrows on either side. But if you happen to run into this guy where it just has 2 letters written back to back like that, that is referring to the distance. So A, B, with nothing over the top of them, means the distance from A to B. That's going to be a length of some kind. Okay, now on basic distances, okay, this is really not all that difficult. Okay, here you have a collection of line segments. There are actually several. You have line segment TQ, line segment QS, line segment QR, line segment TS, line segment QR, and line segment TR. So there's actually a bunch of them in there. We have several measurements that are provided for us in the little spaces in between the points. And you can see over there on the right side, the question just says capital T, capital R equals. Okay, well, remember how you read that. When you have 2 points that are written back to back with no mark over the top of them, that is asking for the length from T to R is, or the distance from T to R is. Well, it's really quite simple. The length from T to R equals the length from T to Q plus the length from Q to S plus the length from S to R. Looking in the diagram, we can see very simply that those measurements are provided for us. T to Q is 3, the length from Q to S is 4, the length from S to R is 6. You add them up, and you've got the length from T to R, 13 units in this case. All right, the last structure in Euclid's geometry is the plane. Okay, plane, new term, goes over on the left side of your paper, and on the right side comes a definition. A plane is an object that exists in second-dimensional space. It has length and it has width, but it has no depth. In general, a plane continues infinitely in both of its directions, and it takes at least 3 non-collinear points to construct a plane. Well, there's one of the definitions that we've already covered, so review that in your mind. What does it mean when they use the word collinear? Collinear means in the same line. So if they say non-collinear, that means 3 points that are not in the same line. As with everything else, when we discuss planes, we call them by their name. Sometimes they will name a plane for us, and they will name it by a capital letter that is somewhere inside of one of the internal corners of the plane, and I'll get to a diagram here in a second. Or we can name it by picking on 3 non-collinear points from the plane. Okay, so from this particular diagram, we have a couple of options. You see in the lower left-hand corner, there is a capital letter just kind of floating there by itself. It is not next to a little dot to make us think that it is a point or anything like that. It's different from point A or point B or point C from the picture. Okay, so that is giving us a name. We can call this guy plane P because they did identify it and gave it a name for us. Or we can pick on any 3 points that are not in a straight line. We have 3 of them. They are not in a straight line. We can call it plane ABC. Okay, and you can use any combination of non-collinear points in the plane. So if there had been more points, we could have used one of them, but you only need 3. You don't go listing off 9 different points if there are 9 different points in the plane. Just 3, and additionally you could have called it plane BAC or BCA or anything like that, but again, alphabetical does tend to be the way that these things are identified. Here's a similar definition to what we saw earlier. If 2 or more things were to exist on the same plane, then they would be coplanar, just like collinear. Collinear meant of the same line. Coplanar means of the same plane. Okay, now we got some basic definitions that you've already heard from Once Upon a Time as well. One of them is parallel lines. Okay. A lot of you had the old definition of that parallel lines are simply lines that do not touch. That is not adequate for what we're going to be working on, because there are plenty of lines in this world that do not touch. That does not make them parallel. Okay. What we need is we need lines that exist in the same plane but do not intersect. There are several ways that we can tell if lines are going to be parallel or not. First, there is a way that they can be identified in the diagram by the person that constructed the diagram. The lines may contain small arrows or triangles that are positioned in the body of the lines. That might look something like this. Wherever you see in a diagram little matching triangles in the body of a line or little matching arrows in the body of the lines, wherever those symbols match up, those things are being identified as being parallel. Another way that we're going to receive information about parallel lines will be by way of external information. Okay, meaning that you may have a diagram, but it may not be marked in the diagram. There might be some extra commentary that's going on outside of the problem. So in this particular case, you have two lines there. We have line M, we have line N, but they did not mark them in the picture, but we look right underneath and we can see some little shorthand symbolic notation, line M, and then you see the little double slash mark in between them. That is a symbol meaning is parallel to, and then you have line N. And the way you'd pronounce that is line M is parallel to line N. Another way that we can be communicated that lines are going to be parallel is by, of course, mathematical information. We're going to study parallel lines quite a bit this year, and if something comes along in the problem, some equation that we're working or some numerical information that we have, basically the math. If there is math in the picture that says that the lines are parallel, then they're parallel. The thing you need to come to grips with is lines are never parallel just because they look like it. And I'll give you a basic example here. Here is a couple of lines. And if I were to ask everybody, are these lines parallel, yes or no? I imagine we would get some conflicted opinions. Some people can look at them and decide, I think they're not parallel. They look like they might be a little closer on one end than the other. Some people would say, yes, they are. And again, it's never, oh, because they don't touch. Okay, that's not good enough, because on the lines, I mean, you've got arrows on both ends. A line continues infinitely in both directions. Okay, well, in this small space, the lines do not appear that they will intersect. Well, like I said, they go on infinitely in both directions. So what if you were to extend them infinitely? And of course, I can't extend them infinitely on my screen here, but have a look at them now. These are the exact same two lines positioned exactly the same way, but look at what is happening over on the right side of the screen. If I had a little bit more space and could continue this off the side of the screen a little bit, it's pretty clear these lines are going to cross each other. So you can see now that they are not parallel. Looks can be deceiving, but we will always need a better reason to decide parallel or not than because they look like it. This is the kind of information you might choose to put in your notes or not, okay, when we're kind of proving a point like we were right here on the parallel lines. If some people will learn it better by writing it down, and that's great. Absolutely write it down. But if you feel like you've got a grasp on it, this may have been something that does not necessarily need to be copied. It's up to you. Okay, another definition which you might have heard over the years, but if you haven't, here it is. Lines that do not exist in the same plane and do not intersect are called skew lines. This is the problem with that old junior high definition that a lot of y'all had with parallel lines, where you just said, hey, parallel lines don't touch. Well, there are plenty of lines in this world that do not touch. That does not make them parallel. They may be skew. Okay. And just a little side note here, it is very difficult to draw skew lines on a two-dimensional piece of paper or a two-dimensional screen. Okay, and here is what an example of skew lines might look like in a diagram. We have a plane, this green guy that's in the middle, and line B exists inside of the green plane. We know that it exists inside of the plane because it does not intersect the plane. There is not a point marked or anything like that on line B that would suggest that it's actually making contact with the plane. On the other hand, line A, we can see that line A clearly intersects the plane. It comes downward towards the plane, then there is a point marked, indicating that it has made contact with something, and then you see the little dotted lines that are kind of hiding. Okay, dotted lines are used in geometric drawings when we know something is there, but our vision is being blocked by something else. In this case, line A comes downward, hits the green plane, and then proceeds through the green plane, but we cannot actually see the line again until it emerges from the bottom side or the front edge of that green parallelogram that's representing the plane. Okay, so these are an example of skew lines. They do not touch, and they are clearly not parallel. That makes them skew. Okay, so line A passes through the plane while line B is in the plane. Since the lines do not intersect and they are not parallel, then they are skew. Okay, just a last few little points here. When two lines, rays, or line segments intersect, they intersect to form a point. This is a pretty obvious point right here because line C and line D, they will not ever bend back toward each other and make contact again. Once they have made that contact, they are done. They're going to continue. Line C in both directions. Line D, since it's a ray, will only continue in one direction, but they're never going to come back and make contact again. Okay. And I missed it, but the way you would pronounce that first diagram is line C and line segment D. Oh, it should be ray D instead of line segment D. And they intersect at point E. Now, when a plane and a line, ray, or line segment intersect, they also intersect to form a point. Okay, you have plane G. Plane G is just a surface. Then here comes line segment F, and it runs through this surface at point H. Is line segment F ever going to bend and come back to get plane G again? No, it's made contact once at a single point. That's all. And lastly, if you have the instance where two planes, two surfaces run across each other, the intersection of those guys will form a line. Now, if you look in the diagram, it's very easy to think that, wait a minute, Mr. Hill, line T is not a line. It's a line segment. See, it doesn't go infinitely in both directions. But think about a plane. Does a plane stop? Does it actually have boundaries like we've drawn in here? Or does it continue infinitely in both of its directions? It does continue infinitely in both of its directions. So if plane R continues coming forward towards us and plane S also continues towards us, then that is going to make line T, the intersection, it's going to make it continue to come towards us as well. Plane R is never going to stop. Plane S is never going to stop. Thus, the intersection is never going to stop either. So it is a line, not a line segment, even though it does look like a line segment in the diagram. And the way you'd pronounce that is plane R and plane S intersect at line T. Okay, you have completed the note-taking portion of your lesson for tomorrow. Guys, this is the way it's going to be for the first couple of months in geometry. There's a lot of definitions, a lot of terminology, a lot of vocabulary and stuff like that. So our notes are going to take a little bit of time at first. As the year goes on and we get a better knowledge of what we're doing, we're going to start to see more and more math. That will mean fewer notes and more things to practice. But for right now, just kind of get adjusted that the notes are going to take a little bit. When you come to class tomorrow, we're going to do some things, answer some questions, do a little activity that'll help us better understand Euclid's geometry and points and lines and planes. Thanks for watching.